Today we will prove Wilson's theorem by group action. So there are a lot of proofs of Wilson's theorem is available, but I think this proof uh, will be interesting. So Wilson's theorem. Um, for a prime p, we have p minus 1 factorial is congruent to minus 1 mod p. So we know if a group act on a set X and if G is a P group, that means G has orders P to the power some n, then the order of X is congruent to the number of fixed point mod P. So we will use this idea to show Wilson's theorem. So let us consider the action of Zp on P cycles in SP. So you know SP is the group of SP is the permutation group with P elements. But taking the P cycles, so we are taking the collection. Let us define the collection SP prime is a collection of P cycles in SP. So P cycles are of the form x0, x1 up to xp minus 1. And we assume that SP is the permutation group with P elements, and the P elements are 0, 1, 2 up to P minus 1. So I will explain later why we are taking this set or this collection. So it will help to define the action of Zp on SP prime. So define the action. Zp cross SP prime to SP prime. Take an element in Zp, let's say k, and take a P cycle from SP prime. Just send this pair to x0 plus k, x1 plus k up to xp minus 1 plus k mod p. So for let us give you an example. So for this cycle for this cycle 0, 1, 2, 3 up to p minus 1. So the action of the trivial element, the generator of Zp, action of 1 is just 1, 2, 3 up to p, and we are defining mod p, so which is 1, 2, 3 up to p minus 1, and replace p by 0 because we are defining this action mod p. Okay, so now let us just compute order of SP prime. So order of SP prime. So as we defined that this is a set of all collections or set of all P cycles. So what is the number of these cycles? So the number is if you fix the first coordinate. So yeah, and this cycles has a property we know. So x1 x0 x1 x2 up to xp minus 1 is just same as, it is same as xi plus 1 up to this thing. I mean in for pre equal to 3, this 0 1 2 cycle is same as 1 2 0. So this is the case. Okay, so the point is, for counting the number of sp prime, you have to fix first coordinate x naught, and you have to permute the other p minus 1 elements. So you have to permute, so permute the p minus 1 elements. So what is the number? It is p minus 1 factorial. So the order of sp prime is p minus 1 factorial. Okay, so now let us compute the order of sp prime g. So let us denote as the number of fixed point of this action. So fixed point means an element, a cycle from this guy sp prime that is fixed by every element in zp. So in particular it is fixed by the element 1. So let's say, what is the action of 1 on x0 up to xp minus 1? The action of 1 is it sends to x0 plus 1 x1 plus 1 dot 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 xp minus 1 plus 1 mod p. Okay, now if this is a fixed element, so if x0 up to xp minus 1 is a fixed element, then x0 up to xp minus 1 has to be equal to x0 plus 1 x1 plus 1 up to xp minus 1 plus 1. So among these numbers, so x0 up to xp minus 1 are distinct numbers modulo p. So among these numbers x1 plus x0 plus 1 x1 plus 1 dot xp minus p minus 1 plus 1, there exists one I inside 0 and p minus 1 such that xi plus 1 is x0, right? So as we noticed before that this is xi plus 1 comma xi plus 1 plus 1, because as we noticed before, this cycles has this property xi plus 2 plus 1 and so on. Okay, this is exactly equal to that. Okay, okay, now if x not equal to xi plus 1, then x1 has to be xi plus 1 plus 1, right? Yeah, because these are equal. Okay, so so in general xk is xi plus k plus 1 mod p. Okay, so what does that means? What does that means? That means x naught minus x1 equal to xi minus xi plus 1, right? Is that clear? With no, every element is fixed by every element in SP prime is fixed by the action of zero element in ZP. So we just say that x naught minus x1 is same as xi minus xi plus 1, right? Similarly, x1 minus x2 is same as xi plus 1 minus xi plus 2. Okay, so iterating this process, you can just say so you can see easily, so you can see easily that the differences the consecutive difference xk minus xk minus 1 is constant. Okay, for all k. For all k inside 1 and p. Okay, yeah, here you have to treat xp as x naught. Okay, so by this you can say that every difference is same. So first of all, here you can notice that if this happens, x not equal to xi plus 1, I is not equal to 0, because then x not equal to x naught plus 1, which is not possible. So yeah, you get that. So the invariant elements, okay, so the elements which are invariant under the action of ZP are 0, k, 2k, dot p minus 1, k, mod p, where k lies inside 1, 2, dot p minus 1. So these are the invariant element. These are the set of all fixed points. So how many are there? So there k varies between 1 to p minus 1. So the number of fixed points, more precisely SP prime G, the number is exactly p minus 1. So now apply the theorem. So order of SP prime is congruent to order of the G fixed elements mod p. So here GZP. So what is the number of SP prime, which is p minus 1 factorial, and what is the number of SP prime ZP is p minus 1, right? And this will imply p minus 1 factorial is congruent to minus 1 mod p. Yeah. This is the Wilson's theorem. Thanks for watching. See you on next video.